Alright, so we're going to look at Prolog for just a little bit. I have no idea if this book will take us into typing Prolog quickly, but I really hope so, because I really like it when you learn something and you're typing very early on. I've seen this book cover before, and I just like Japanese art, so it's really cool. I just hope the book's as good as the art. So let's see. We'll probably need to install a Prolog interpreter also. Copyright 1986, 1994. So it's been a while, almost 30 years now, or longer if you count the first one. Facts, queries, logical stuff. All right. It's a big book with almost 500 pages. Wow. Look at our friend Quicksort somewhere up here I just saw, right? Quicksort using difference lists. ELIZA. Connectivity. Finding a path by depth first search. This is cool. Alright, we have a nice forward here. We're going to use logic as a programming language. Oh, this is probably too small for you guys. Let's see how it looks. Forward. Should we read this? Let's see how long it is. It's not too long. Programming in Prolog opens the mind to a new way of looking at computing. There's a change of perspective which every Prolog programmer experiences when first getting to know the language. I shall never forget my first Prolog program. The time was early 1974. I had learned about the abstract idea of logic programming from Bob Kowalski at Edinburgh, although the name logic programming had not yet been coined. The main idea was that deduction could be viewed as a form of computation, and that a declarative statement of the form P if Q and R and S could also be interpreted procedurally as to solve P, solve Q and R and S. Now I have been invited to Marseille. Here, Alain Colmero. Is this a French name? Marie. Oh, sorry. How would you pronounce this name? Is this French?
Colmeroer.
Colmero. How?
Colmeroer.
Colmeroer. Colmeroer and his
Oui.
colleagues had devised the language Prolog based on the logic programming concept. Somehow, this realization of the concept seemed to me at first sight too simple-minded. However, Gerard Bottini and Henri Meloni had implemented a Prolog interpreter in Fortran, their first major exercise in programming incidentally. Why not give Prolog a try? I sat at a clattering teletype. Do you guys know what teletype is? It's like one of those retro things. Teletype. There you go. Teletypes. I think this was like old style IRC or something. I have never had the chance to play with a teletype. Alright. I sat at a clattering teletype connected down an ordinary telephone line to an IBM machine far away in Grenoble. Oh, so it is France. I typed in some rules of defining how plans could be constructed as sequence of actions. There was one important rule modeled on the SRI planner strips, which described how a plan could be elaborated by adding an action at the end. Another rule necessary for completeness described how to elaborate a plan by inserting an action in the middle of the plan. All right. Prolog spat back to me. Question mark? Meaning it couldn't find a solution. Could it be that a solution was not deducible from the axioms I had supplied? Ah, yes, I had forgotten to enter some crucial facts. I tried again. Prolog was quiet for a long time and then responded, Débordement de pile. Stack overflow. I have run into a loop. Now, a loop was conceivable since the space of potential plans to be considered was infinite. However, I had taken advantage of Prolog's procedural semantics to organize the axioms so that shorter plans ought to be generated first. Could something else be wrong? After a lot of head scratching, I finally realized that I mistyped the names of some variables. I corrected the mistakes and tried again. Lo and behold, Prolog responded almost instantly with the correct plan to achieve the goal state. Magic! Declaratively correct axioms had assured a correct result. Deduction was being harnessed before my very eyes to produce effective computation. Declarative programming was truly programming on a higher plane. I had dimly seen the advantages in theory, now Prolog had made them vividly real in practice. Never had I experienced such ease in getting a complex program coded and running. Of course, I had taken care to formulate the axioms and organize them in such a way that Prolog could use them effectively. I had a general idea of how the axioms would be used. Nevertheless, it was a surprise to see how the axioms got used in practice on particular examples. It was a delightful experience over the next few days to explore how Prolog actually created these plans, to correct one or two more bugs in my facts and rules, and to further refine the program. Since that time, Prolog systems have improved significantly in terms of debugging environment, speed, and general robustness. The techniques of using Prolog have been more fully explored and are now better understood, and logic programming has blossomed, not the least because of its adoption by the Japanese as a central focus of the fifth generation project. So, oh, well, and some more. Above all, the book conveys the excitement of using Prolog, the thrill of declarative programming. As the authors put it, declarative programming clears the mind. I could surely use some mind clearing. Oh my. Even more. Let's see if there's anything. So a lot has changed. While not widely used as C, this is like seeing like what happened later. It's like the epilogue of a story. And the main character died a tragic death. Prolonger is no longer regarded as an exotic language. Kinda is. An abundance of books on Prolog have appeared. Prolog is now accepted by many as interesting and useful for certain applications. Alright. We will go on now. This was written in Cleveland. Preface to the first. They got a lot of preface. Alright, so here's the introduction. Introduction. You guys know that like the Unreal Engine has a language that they're adding called Verse for their kind of like multiverse programming. And it has like both it's both like has functional roots but also logical roots. So it's a little bit like a mix of like something like Haskell and Prolog put together. So it's really interesting to see that, you know, these logic ideas, logic programming ideas are sort of being used in modern languages. Anyway, 553 pages. It's kind of long, right? We don't have to read through all of it tonight. You guys see that up here, right? Oh, yeah. The inception of logic is tied with that of scientific thinking. Logic provides a precise language for the explicit expressions of one's goals, knowledge, and assumptions. Logic provides the foundation for deducing consequences from premises, for studying the truth or falsity of statements, giving the truth or falsity of other statements. We don't say falsity very often. For establishing the consistency of one's claims, and for verifying the validity of one's arguments. Computers are relatively new in our intellectual history. Similar to logic, they are objects of scientific study and a powerful tool for the advancements of scientific endeavor. Like logic, computers require precise and explicit statement of one's goals and assumptions. Unlike logic, which has developed with the power of human thinking as the only external consideration, the development of computers has been governed from the start by severe technological and engineering constraints. Although computers were intended for use by humans, the difficulties in constructing them were so dominant that the language for expressing problems to the computer and instructing it how to solve them was designed from the perspective of the engineering of the computer alone. Almost all modern computers are based on the early concepts of von Neumann and his colleagues, which emerged in the 1940s, which is very much like imperative programming. The von Neumann machine is characterized by a large uniform store of memory cells and a processing unit, with some local cells called registers. The processing unit can load data from memory to registers, perform arithmetic or logical operations on registers, and store values of registers back into memory. This sounds a lot like assembly language, the one we're doing with 6502. A program for a von Neumann machine consists of a sequence of instructions to perform such operations, and an additional set of control instructions which can affect the next instruction to be executed, possibly depending on the content of some register. So like branching, stuff like that. As the problem of building computers were gradually understood and solved, the problems of using them mounted. The bottleneck ceased to be the inability of the computer to perform the human's instructions, but rather the inability of the human to instruct or program the computer. A search for programming languages convenient for humans to use began. Starting from the language understood directly by the computer, the machine language, better notations and formalisms were developed. The main outcome of these efforts was languages that were easier for humans to express themselves in, but that still mapped rather directly to the underlying machine language. Although increasingly abstract, the languages in the mainstream of development started from assembly language through Fortran, Algol, Pascal, and Ada. All carried the mark of the underlying machine, the von Neumann architecture. This is not quite true for Lisp, by the way, and it was also an early language with these guys. No Lisp mentioned. Very disappointing. To the uninitiated intelligent person who is not familiar with the engineering constraints that led to its design, the von Neumann machine seems an arbitrary, even bizarre device. Thinking in terms of its constrained set of operations is a non-trivial problem which sometimes stretches the adaptiveness of the human mind to its limit. Which is really funny because basically the argument against using a lot of these functional programming languages these days is that just doesn't seem intuitive. People find it's a lot more intuitive to think, get this from this memory, do something with it, store it back in memory. You know, it's very much like telling it what to do. These characteristic aspects of programming, von Neumann computers led to a separation of work. There were those who taught how to solve the problem and designed the methods for its solution, and there were the coders who performed the mundane and tedious task of translating the instructions of the designers to instructions a computer can use. Both logic and programming require the explicit expression of one's knowledge and methods in an acceptable formalism. The task of making one's knowledge explicit is tedious. However, formalizing one's knowledge in logic is often an intellectually rewarding activity and usually reflects back on or adds insight to the problem under consideration. In contrast, formalizing one's problem and method of solution using the von Neumann instruction set rarely has these beneficial effects. So how I read this is basically like it's a lot of fun to kind of think about the logic that's involved, what you know, what you don't know, and how how it kind of works. But formalizing the problem, that is to basically say like, all right, here's how you solve the problem in a more of a constructive manner, is a lot less fun. So I think a lot of people would argue that's not true. But definitely I think a lot of people who are more academic and into math and whatever would agree with this. We believe that programming can be and should be an intellectually rewarding activity, that a good programming language is a powerful conceptual tool, a tool for organizing, expressing, experimenting with, and even communicating one's thoughts. That treating programming as coding, the last mundane, intellectually trivial, time consuming, and tedious phase of problem solving a problem using a computer system is perhaps at the very root of what has been known as the software crisis. I don't know about this. This is probably something that happened before. When do we start learning? Rather, we think that programming can be and should be part of the problem solving process itself, that thoughts should be organized as programs so that consequences of a complex set of assumptions can be investigated by running the assumptions, that a conceptual solution to a problem should be developed hand in hand with a working program that demonstrates it and exposes its different aspects. Suggestions in this direction have been made under the title Rapid Prototyping. It's funny to think of Prolog as rapid prototyping. To achieve this goal in its fullest, to become true mates of the human thinking process, computers still have a long way to go. However, we find it both appropriate and gratifying from a historical perspective that logic, a companion to the human thinking process since the early days of human intellectual history, has been discovered as a suitable stepping stone in this long journey. Although logic has been used as a tool for designing computers and for reasoning about computers and computer programs since almost their beginning, the use of logic directly as a programming language termed logic programming is quite recent. Hey, Paolo. We are reading. Let's see, we're on page 44, right? We are reading The Art of Prolog, trying to learn little logic programming. All right. How are you doing, Paolo? Logic programming, as well as its sister approach, functional programming, hey, sort of Lisp almost mentioned, departs from departs radically from mainstream of computer languages. Rather than being derived by a series of abstractions and reorganizations from the von Neumann machine model and instruction set, it is derived from an abstract model which has no direct relation to or dependence on to one of the machine model or another. It is based on the belief that instead of the human learning to think in terms of operations of a computer, that which some scientists and engineers at some point in history happened to find easy and cost effective to build, the computer should perform instructions that are easy for the humans to provide. In its ultimate and purest form, logic programming suggests that even explicit instructions for operation not be given, but rather that the knowledge about the problem and assumptions sufficient to solve it be stated explicitly as logical axioms. For college stuff. Cool, I'm thinking about learning Prolog too. Yeah, actually, it's funny because the way I got into this was because there's an actual company that I was talking to, and they use Prolog and Clojure which is like Lisp. And so, like, if I work with them or help them out, like, I just wanted to know some Prolog, but also just it was always interesting to me. I had no idea that people were using it in industry. But guess so. Such a set of axioms constitutes an alternative to the conventional program. The program can be executed by providing it with a problem, formalized as a logical statement to be proved, called a goal statement. The execution is an attempt to solve the problem, that is, to prove the goal statement, given the assumptions in the logic program. A distinguishing aspect of the logic used in logic programming is that a goal statement typically is existentially quantified. It states that there exist some individuals with some property. An example of a goal statement is there exists a list X such that sorting the list 3, 1, 2 gives X. Okay, cool. Which would be 1, 2, 3, right? The mechanism used to prove the goal statement is constructive. If successful, it provides the identity of the unknown individuals mentioned in the goal statement. Here, the unknown is X, which constitutes the output of the computation. In the preceding example, assuming that the logic program contains appropriate axioms defining the sort relation, the output of the computation would be X equals 1, 2, 3. Huzzah, I was right. I read an article that was talking about Prolog being used in the Windows kernel, but nothing more. Is this true? Kernel, whoops. So I can't find it. Whoops. But I'm not great at search. Sorry. These ideas can be summarized in the following two metaphorical equations. Ooh, we got metaphors now. Program equals set of axioms. Computation equals constructive proof of a goal statement from the program. The ideas behind these equations can be traced back as far as intuitionistic, I don't know this word, intuitionistic mathematics and proof theory on the early 20th century. They are related to Hilbert's program. I almost read this wrong. To base to base the entire body of mathematical knowledge on logical foundations and to provide mechanical proofs for its theories starting from the axioms of logic and set theory alone. It is interesting to note that the failure of this program, from which ensued the incompleteness and undecidability results of Gödel and Turing, marks the beginning of the modern age of computers. Wow, this is getting very like history, science history, and stuff like that. First Hacker News post. Search Prolog Windows Networking on Google. This one, Hacker News? Microsoft NT. When was NT used? 1993 to oh dude, latest release 2024. Wait, what? What? We're still using Windows NT? What? Are you kidding me? I Wait. Oh, these are all NT. So this is all NT, even the ones that don't have NT? I don't get it. Maybe I'm just confused. The hell? NT continues to exist to this day with incremental changes and improvements, with the latest version of Windows based on Windows NT being Windows Server 2025. Wow. That's crazy. All right. I know this is really small here. NT operating system uses an embedded Prolog interpreter to configure its local and wide area network systems. Independent software and hardware components are abstracted into a simplified object-oriented framework using declarative information provided by each installation script. This information, along with the Prolog algorithm, is consulted into the embedded interpreter, which is then queried to construct the most usable configuration. All right, so it gets like, I can imagine seeing this like used for networking where routing and other things is just like a whole bunch of facts, and then it can kind of like solve for something, like the best way to get somewhere or whatever. That's cool. Well, thanks for sharing that. I did not know that. NT's the kernel still? Well, I'm I don't know this. Yeah, sounds good. All right, so where were we? The first use of this approach in practical computing is a sequel to Robinson's unification algorithm and resolution principle, published in 1965. Several hesitant, very hesitant attempts were made to use this principle as a basis of a computation mechanism, but they did not gain any momentum in the beginning of logic programming that can be attributed to Kowalski and Kolmogorov. How do you say it? Kolmogorov? Kolmogorov?
Je sais pas c'est qui moi.
No, but how did you say it?
It's not French name.
Oh. Kowalski formulated the procedural interpretation of horn clause logic. He showed that the axiom A of B1 and B2 da, 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 and Bn can be read and executed as a procedure of a recursive programming language where A is the procedure head and Bi are its body. So procedure head meaning like in lambda calculus, it's the head, it's the parameters, and this is the body. So it's basically executing all of this. In addition to the declarative reading of the clause A is true if Bi are true, it can also be read as follows: to solve, execute A, solve, execute B1 and B2, so forth, up to Bn. In this reading, the proof procedure of horn clause logic is the interpreter of the language, and the unification algorithm, which is at the heart of the resolution proof procedure, performs the basic data manipulation operations of variable assignment, parameter passing, and data selection, and data construction. All right, so this is a bit of history. I think we can pass some of this, if you will forgive me. All right. Oh, look, who's this? Like, is this Socrates or someone? Old man thinking. It's just Leonardo. It's just Leonardo da Vinci. All right, what does this say? 1. Logic programs. A logic program is a set of axioms or rules defining relations between objects. A computation of a logic program is a deduction of consequences of the program. A program defines a set of consequences which is its meaning. The art of logic programming is in constructing concise and elegant programs that have the desired meaning. Okay. Basic constructs. The basic constructs of logic programming, terms and statements, are inherited from logic. There are three basic statements: facts, rules, and queries. Okay, guys, remember that. Facts, rules, and queries. There is a single data structure, the logical term. The simplest kind of statement is called a fact. Okay, so there's facts, rules, and queries. So the simplest is facts. Facts are a means of stating that a relationship holds between objects. An example is Father Abraham Isaac. When are we going to type stuff? Hold on a second. What page is that? 54? Because if we're not going to type anything, I might as well just make this full screen. When do we type? Guys, come on. Maybe we're not typing. Maybe we're supposed to type the stuff from the very beginning. Yeah, I think we probably could. Was it 54? Facts are a means of stating. So let's see if we can enter a fact. Oops. Do we have Prolog? We have a Prolog in here. I don't know what all of this is. Oh, I think this was just like a failed attempt at Prolog. Alright, so we will next shell minus p, what is it called? SWI Prolog. SWI Prolog. That should get us Prolog. And this will give us SWI-PL. How to enter facts in SWI Prolog. I just want to see. SWIPL. Wow, it takes a while to start up Prolog. What's it doing? Alright, here we go. So what do we say here? Basic constructs is a fact. A fact are means of stating that a relation. Example is father. Maybe we could just type this. Let's see. Father Abraham, comma, Isaac. Getting all biblical. Oh no, it doesn't work. A fact says that Abraham is the father of Isaac, or that the relation father holds between individuals named Abraham and Isaac. Another name for a relation is a predicate. Names of individuals are known as atoms. Similarly, plus 2, 3, 5 expresses the relationship that 2 plus 3 is 5. Oh, okay. The familiar plus relation can be realized via a set of facts that defines the addition table. An initial segment of the table is 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 1 is 1, and so forth. A sufficiently large segment of this table, which happens to be also a legal logic program, will be assumed as the definition of the plus relation throughout this chapter. The syntactic conventions used throughout this book are introduced as needed. The first is the case convention. It is significant that names of both predicates and atoms begin with the lowercase letter rather than an uppercase letter. So you have Father, Tarak, Abraham. A finite set of facts constitutes a program. This is the simplest form of a logic program. A set of facts is also a description of a situation. This insight is the basis of database programming to be discussed in the next chapter. An example database of family relationships from the Bible is given as program 1.1. The predicate father, mother, male, female express the obvious relationships.
What?
Yeah, I know. What? What I'm trying to do is, how do I enter this into SWI Prolog? Let's see here. Documentation, like,
What the fuck is this? Oh là là, oui.
doesn't it seem like I should be able to type in likes
Oui,
John, comma, Susie, just like they say here?
J'ai vu, je me suis dit, c'est quoi ce truc? J'ai pas
Creep,
des
what?
noms de gemmes, livraison. C'est 2 montures et des ailes, 100 000 gemmes. Ça fait 7100.
Ah, we might need rules. Friends, XY
Oh
likes.
putain.
But these are facts. Maybe it's that it needs to be in a file?
Oh non, non, c'est chaud là. C'est chaud. Et encore, j'en ai déjà des.
Let's try adding it into a file and seeing if this works.
J'ai déjà fait parce que j'ai clairement pas un seul euro. Oh putain.
We'll say test.pl for Prolog, and we'll just say father Abraham, comma, Isaac. Dot. And now we try SWIPL, right? And how did they do it here? Can use Prolog as a REPL. That's what I was hoping for. Looks like we're trying to run. What the hell? The following goal loads the file likes.pl. Okay, so I can do like this. Oh, no. I can type it in here. Test.pl. Okay, great. So that actually loaded my test file, I guess. So I have this in my test file. So now, can I actually ask it this? Or is this true? I guess I asked it that. False. Hey, we're getting somewhere. We're getting somewhere. Let's go. This fact says Abraham. Yeah, we read all that. And then we have all of these, which I don't know. Do I want to type this in? Are we going to use it? Yeah, it looks like we're going to have to use it. So this is going to be a little bit of an annoying thing. We're going to call this family database. I guess like we can just kind of like 1, 2, 3, 4, 5, 6, 7. Is it 7 of these guys? And we're gonna put Prolog here.
Il en a déjà pas mal.
I forget how in Helix I do this.
C'est quoi ça, date with destiny?
How did I forget this?
Ah, c'est les fates.
Oh well, we'll have to do it the stupid way.
Ah putain, mais je suis con, c'est marqué en dessous ce que c'est.
Haran?
Aléa.
Haran, right? Abraham, Nahor, Haran, Isaac, Lot, Milcah, Yiska, mother Sarah, Isaac, Terak, Abraham, whoops, Nahor. I cannot type. I'm so sorry. I'm so bad.
Ah, c'est celui que je veux faire.
I think the arguments of the function thingy needs to be capitalized. I think we got through that. Alright, we have our program. Let's save this before we forget. Family.pl. Okay. It probably thinks this is Prolog. It's alright though. So now we got our first Prolog. Well, this is technically second Prolog program. The second form of statement in a logic program is a query. Queries are a means of retrieving information from a logic programming. A query asks whether a certain relation holds between objects. For example, the query father Abraham Isaac asks whether the father relationship holds between Abraham and Isaac. Given the facts of program 1.1, the answer to this query is yes. So let's see if we can load this. SwePL family.pl. It loaded this, and now I can say father Abraham, comma Isaac. No, question mark comes at the end. Oh no, it doesn't like this. That's kind of funny, huh? I guess the way I did it last time was like with a dot. So I did father Abraham Isaac. dot, and it said true. But why does it say question mark here? Syntactically, queries and facts look the same, but they can be distinguished by the context. No, they don't look the same because look, you got a question mark here. I don't understand. Like, these guys aren't making sense now. When there is a possibility of confusion, a terminating period will indicate a fact, while the terminating question mark will indicate a query. We call the entity without a period or question mark a goal. A fact P states that the goal P is true. A query P question mark asks whether the goal P is true. A simple query consists of a single goal. So you're saying I can just say Father Abraham, comma Isaac without anything? No. Like Sam, comma X. Dot. X equal semicolons. Yeah, I don't know. It looks like it's different. This is the problem, isn't it? Alright, anyway, at least we kind of got, we just type in the fact and it says false. Answering a query with respect to a program is determining whether the query is a logical consequence of the program. We define logical consequence incrementally through this chapter. Logical consequences are obtained by applying deduction rules. The simplest rule of deduction is identity. From P deduce P. A query is a logical consequence of an identical fact. Operation, so it's just like if you say something like X is true or, whatever, X is a dog, and you just say, hey, is X a dog? It's like, just doesn't need to look anything up. It just is. Operationally answering simple queries using a program consisting facts like program 1.1 is straightforward. Search for a fact in the program that implies the query. If a fact identical to the query is found, the answer is yes. So it's basically looking up does this exist in our program, and it's true. It does exist, so it's kind of trivially true. The answer no is given if a fact identical to the query is not found because the fact is not a logical consequence of the program. This answer does not reflect on the truth of the query. It merely says that we failed to prove the query from the program. Both the queries female Abraham and plus 1, 1, 2 will be answered no with respect to program 1.1. False. Yeah, it's a syntax issue. Was it Sarah? Okay. Whew, this Prolog thing has been a little bit slow. A little bit difficult. A logical variable, if we can get through this, then we're good, I think. Because right now, all we've done is like super simple stuff. A logical variable stands for an unspecified individual and is used accordingly. Consider its use in queries. Suppose we want to know of whom Abraham is the father. One way to ask a series of queries: Father Abraham Lot, Father Abraham Milcah, etc. Father Abraham Isaac, until an answer yes is given. We basically want to know is Lot the father of Abraham, right? So we just try everything. A variable allows a better way of expressing the query as father Abraham comma x, to which the answer is x equals Isaac. Let's try that out. So you can see here that Abraham is the father of Isaac, right? So if we put x in here, then it should tell us Isaac. How do I do this? Isaac, right? Oh, I have to tell it which program to use. Family. And then I do father Abraham, comma x. Maybe like this? Question mark? No, that was not right. Ah! Father Abraham, comma x. Maybe I do it as a dot. Oh, here, it is a dot. X equals Isaac. So that's cool. It actually did something for us. To which the answer is x is equal to Isaac. Used in this way, variables are a means of summarizing many queries. Does that mean I can do female x? Why did it just give me 1 though? Oh, if I press space, it gives me more options. That's pretty cool. There's probably a way for me to like say and then I can kind of like combine them together. Used in this way, variables are a means of summarizing many queries. A query containing a variable asks whether there are the value. Yeah. Variables in logic programs behave differently from variables in conventional programming languages. They stand for an unspecified but single entity rather than for a store location in memory. Having introduced variables, we can define a term, a single data structure in logic programs. The definition is inductive. Constants and variables are terms. Also, compound terms or structures are terms. A compound term comprises of a functor called the principal functor of the term and a sequence of one or more arguments, which are terms. A functor is characterized by its name, which is an atom, and its arity, the number of arguments. Syntactically, compound terms have the form f t1 t2 to tn, where the functor has the name f and is of arity n, and the ti are all the arguments. Yeah, so this is very similar to Elixir and Erlang, where like functions have arities and you refer to it by its arity. So you're like, oh, I'm looking for, like ID/3, which means I'm looking for the ID function that takes in 3 parameters. Example of compound terms include S with 0, hot with milk, etc. Queries, goals, and more generally terms where variables do not occur are called ground. Where variables do occur, they are called non-ground. For example, foo a comma b is ground, whereas bar x is non-ground, because all these are symbols, or whatever you call them. They're like atoms. So they're lowercase, and that's why they said all of those have to be lowercase, but uppercase are variables. So this is non-grounded. Are you guys following any of this? Does this make any sense to anyone? Alright. Definition. A substitution is a finite set, possibly empty, of pairs of the form xi is equal to ti, comma, where xi is the variable and ti is the term. And xi does not equal xj for every I does not equal xj, and xi does not occur in tj for any I and j. An example of a substitution consisting of a single pair x equals Isaac. Substitutions can be applied to terms. The result of applying a substitution theta to term A denoted by A theta is the term obtained by replacing every occurrence of x in T by T in A for every pair x equals T in theta. The result of applying x equals Isaac to the term father Abraham, comma x is the term father Abraham Isaac. Okay, I think we can kind of like unpack this a little bit, but basically you're going to pass in stuff and then you replace it here. It feels a lot like lambda calculus. A substitution finite set of pairs of the form xi equals ti. So we can have a bunch of these pairs. X equals Isaac, whatever, y is equal to something else. And so all the capitals are the variables, so that's why xi is a variable. So the left side is a variable. And on the right side is a term. And xi does not equal to xj, which means there are no repeats for every I that doesn't equal j. And xi does not occur in tj. So none of the terms have the same variable. Makes sense?
What?
Definition. A is an instance of B if there's a substitution theta such that A is equal to B theta. Oh yeah, they were talking about B theta. 1 second. I gotta find what that meant here. Okay, so when we apply substitution theta to term A, this is the substitution, right? We call it A theta. So here it's basically saying, is there any substitution that can basically turn A into B? Right, right. So that's basically trying to say, is there a solution for this question? The goal father Abraham Isaac is an instance of father Abraham, comma x by this definition. Similarly, mother Sarah Isaac is an instance of mother x, comma y under the substitution x equals Sarah, y equals Isaac. So yeah, there exists a substitution for which you can make this true. So we have to remember some of these things, like A is an instance of B. So B is going to be a little bit more general because it has variables, right? So like here you see instance of mother x comma y, that is a B here, and the theta is the x and y here. So I get that.
Love the dedication to avoiding dragon spotting, my first pair job in quest in top of there.
Maybe this is a good place to stop for now because we have these existential queries. Likes. Definition. I wish this thing was a lot more like interactive, you know, like if you start learning Rust or anything, they have you like doing stuff, but this text, it's supposed to be really good, but like we're writing very little code, which is a little like, how are you supposed to learn the language? It's about an hour now that we've been on. No, actually, an hour and 42. Well, What does that mean? Is this like
I know.
scamming stuff or what? What does that mean? Boa. Boa tarde. PTBR. So, thanks for hanging out with me during this prologue, my little prologue fix that I wanted to, the little itch that I had to scratch. We didn't get very far, but hey, we got like some basic stuff going on. We kind of learned how to make a Prolog program like here. And then we learned how to do simple queries like, hey, show me like Sarah is the mother of Isaac, right? So that means we can say mother. Sarah is the mother of who? And it'll say Isaac, right? So we've learned some of this stuff. And I wish I knew how to say and I don't know. But I don't know the syntax for this. Yeah. I don't know how to say and. But that would be kind of cool too. Or we can say female X, right? Like that would be kind of like, does she have a daughter, basically, is what this is saying, right? But I don't know how we say that yet.
Maybe they should update this job.
So, oh, query comma. Looks like maybe it's a comma.
Ça n'a aucun sens.
Oh, this is cool. There we go. So let's see if we can come up with something more complicated then. What was there? Like, I want to know. Mother. Sarah's the mother of Isaac. Father. So I want to say, like, who are the daughters of Haran, for example, right? So we have Lot, who's a dude, Milka, who's a woman, and Yiska's female. So if I want just the daughters, I'll get Milka and Yiska, right? So let's see if we can run that. So I want to say where Abraham is the father, so it's a child of Abraham, and the child is female. What are you learning? Give me some context. This is Prolog. Nikhil. What? Oh no, it wasn't Abraham, it was Haran. Sorry about that. There we go. Milka and Yiska. You see that? That's awesome, right? So, whoops. We have all these facts that Prolog can take in. These are the facts. And then we're able to run queries, which are like logical queries. And supposedly logical programming is Turing complete. We can do everything like sort, whatever. I just wanted to learn more about Prolog to kind of like figure out how that works. So we're only at the very beginning. What is Prolog? Oh my god. Well, we're at the end of this stream, but like Prolog is basically, well, why doesn't this go here? Come on. Prolog is a programming language. It's one of the very early programming languages. And I had a kind of like, not really job interview, but like I was talking about working with a company, and like I found out they use Prolog. They use Prolog and Clojure. And I was like, oh, people use Prolog at, in companies. So I was like, oh, well, I should learn a little bit of it. I learned about it in university, but I never really programmed in it at all. I kind of did the very basics. So yeah, so I was like, okay, well, I never got my mind wrapped around how you could possibly use a logical programming language to do most things. Like functional, I get. Imperative, I get. But like, how are you supposed to do, how are you supposed to do this with logic only? So That's what Prolog is about. And this will be saved as a stream so you can, go to the beginning of it and see what, because we read a lot about what Prolog is and the history behind it. So maybe I'll do more Prolog later, but whatever happens, happens. Thank you for hanging out, and I will talk to you all later. Have a great day, evening, wherever you are. See you soon. Bye.